What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the problem of building robust AI systems, specifically in the context of developing superhuman Go agents that are resilient to adversarial attacks. The paper focuses on defending against adversarial attacks in Go by studying different defense strategies, such as adversarial training with hand-constructed positions, iterated adversarial training, and using a vision transformer, VIT, instead of a convolutional neural network, CNN. These defenses aim to make the AI agents minimally exploitable by adversaries, ensuring that they cannot be easily defeated or manipulated to make game-losing blunders that a human would not make. The goal is to increase the robustness of AI systems, making it harder for adversaries to find successful attacks with minimal computational resources. The paper highlights the challenges of achieving complete robustness, as none of the defenses provided in the study make attacks impossible, but rather make them more difficult and computationally expensive to execute successfully.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method in the paper works through an iterative process called iterated adversarial training. This process involves training a victim agent and an adversary agent alternately, over multiple rounds, to defend against a broader range of attacks. The victim is initially trained to be robust against the latest adversary, and then an adversary is trained to attack this hardened victim. This process is repeated for multiple iterations, with each iteration involving training the victim against the latest adversary, and vice versa. The victim is fine-tuned from the previous victim step, while the adversary is fine-tuned using victim play with a curriculum of checkpoints from the previous victim step. The training continues until the victim's win rate plateaus, or a set maximum compute budget is reached. This method aims to create a robust agent by repeatedly defending against new attacks until the space of possible attacks is exhausted. The results show that each defender learned an effective defense against the simulated adversary, but rarely reached a 100% win rate, indicating partial protection against attacks. The final victim remains vulnerable even at high visits, showing that while the method makes attacks harder, it does not make attacks impossible, highlighting the challenge of defending against all possible attacks in the domain of Go.
What are the theoretical or practical benefits of using this method?
The theoretical benefit of using the method described in the paper is that it provides insights into the challenges of achieving robustness in AI systems, particularly in the context of adversarial attacks in the game of Go. The practical benefit is that the method allows for the evaluation of defenses against adversarial attacks, such as adversarial training with hand-constructed positions, iterated adversarial training, and using a vision transformer, VIT, instead of a convolutional neural network, CNN. These defenses make attacks harder and increase the amount of compute needed to successfully beat the defended systems. However, the results show that none of the defenses make attacks impossible, highlighting the difficulty of achieving complete robustness. The method also demonstrates the importance of balancing offense and defense strategies in AI systems, as attackers can still find successful attacks with minimal compute. Additionally, the method suggests avenues for future research, such as developing new attack algorithms that require less compute, improving sample efficiency in adversarial training, exploring multi-agent reinforcement learning schemes, and investigating alternative defense strategies like online or stateful defenses.
How is the method validated or tested?
The method is validated or tested by using 3 natural defenses against adversarial attacks in Go: positional adversarial training, iterated adversarial training, and replacing the convolutional neural network, CNN backbone with a vision transformer, VIT backbone. These defenses are tested by training adversaries to exploit the defended systems and evaluating their success rates. The positional adversarial training defense is tested by training new adversaries that beat the strongest Go AI network, showing vulnerabilities despite initial defense. The iterated adversarial training defense involves training a victim and an adversary alternately, resulting in victims that are largely robust to observed attacks but still vulnerable to new attacks. The VIT defense is tested by training a VIT-based Go AI to a superhuman level and evaluating its vulnerability to adversarial attacks, showing that even VIT-based agents are exploitable by new attacks. Overall, the defenses are tested by assessing the effectiveness of each defense in making attacks harder, increasing the amount of compute needed to defeat the defended systems, but ultimately not achieving complete robustness against adversarial attacks.
What results were achieved with this new method?
The new method of iterated adversarial training produced victims that were largely robust to the attacks they observed, losing only a low single-digit percentage of games. However, the victims did not gain robustness to new attacks, as a new adversary could still be trained to exploit the final victim. Each victim achieved a high win rate against the adversary it was trained against when using at least 16 visits of search. The final victim was still vulnerable even at high visits, with the final simulated adversary winning 42% of the time against the victim, even at 65,536 visits. The adversaries exploited a cyclic group, with qualitative variations in the size and location of that group. The results showed that while the defenses made attacks harder and increased the amount of compute needed to beat the defended systems, none of the defenses provided a complete solution, and attacks were still possible with a small fraction of the compute used to train the victims.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method presented in the paper include the inability of the defenses to provide a complete solution against adversarial attacks in the narrow domain of Go. Despite making attacks harder and increasing the amount of compute needed to defeat the defended systems, none of the defenses were able to make attacks impossible. The study showed that the attack algorithm from Wong 2023 adversarial could always find a successful attack with a small fraction of the compute used to train the defended systems. Additionally, none of the defenses achieved the robustness of a human, as humans were still able to execute several attacks against the defended systems. The defenses were also vulnerable to new attacks, indicating that the defenses did not gain robustness to new attack strategies. Furthermore, the method was bottlenecked by the attack component, which took significantly more compute than the defense component in the iterated adversarial training approach. This suggests a need to reduce the time taken to find new attacks to allow for training against a larger corpus of attacks. Overall, the study highlights the challenge of defending against all possible attacks, emphasizing the need for further research and development in the field of building robust AI systems.